Okay, let's start. This is the extra lesson for the cooling load calculation. Now, the cooling load is what you need to keep your room at the set temperature. So let's say we have a heat source, a coffee pot, and it makes a sensible heat load. That's higher temperature from waste heat. And a latent heat load, and that's the need to air condition the water vapor out of the air. Now, if there's no air conditioner, the temperature and the humidity will just keep going up from the heat from this coffee maker. Now, let's say in this case, the heat from the coffee maker is 100 watts, and the steam from the coffee maker is about 200 watts. That means you need 300 watts of air conditioning to counter that. And then the temperature and the humidity will stay stable in the room. So we're going to calculate the amount of cooling you need for a room. And there are many different sources of heat you must counter. There's the heat that comes from the glass, from sunlight, the windows. There's heat from the walls if it's a hot day outside. Heat from maybe from inner walls if the next room is also hot. Heat from infiltration, so any gaps in the windows or in the walls, or maybe there's a door, there might be air coming into the room. Heat from the lights. Heat from any appliances, so computers, heat sources, maybe a kitchen. Heat from the people inside. And the heat that you need from the fresh air that you bring into the room through the air conditioning system. And we'll add an extra factor for losses. Now the latent loads, you need to dehumidify the air if it is more humid. So any air coming from outside in the summer is probably more humid. If your appliances, maybe there's some steam, or in the kitchen, there's some humidity from that. From people, from their breath, and from sweat, there's water vapor from that. And any water vapor in the fresh air we bring into the room. And an extra safety factor. So we're doing a practice problem. This is from a textbook. These are the dimensions of a room. This is north. So this is a northeast corner room with two windows, like this. There's an adjacent room, and another adjacent room. Now, this room, the set temperature for this problem is 26 degrees. And we'll say this next room is also air conditioned to the same temperature, 26 degrees. So there's no heat transfer between these rooms. From here to here, it's the same temperature, so no exchange of heat. But later, this room is a different temperature. And for the problem, we need the dimensions of the room to get the area of the floor, the volume of the room, air volume. We're just doing from the floor to the ceiling here. Above there's a space, but we'll just do this volume. And the area of the windows on the north side and the east side. The area of the walls, don't forget to subtract the window area. So subtract the window area. And the area of this inner wall. We are ignoring this wall because there is no transfer of heat. And the set conditions for this problem. the room temperature of this office will set to 26 degrees at 50% humidity. If you check on the psychrometric chart, the absolute humidity is here. For this problem, we have 0.2 people per square meter in the office space. And we have some ventilation requirement. There's some infiltration through cracks at the windows or doors. There's some lighting load of 20 watts per meter squared. Appliances with 30 watts per meter squared. Sensible heat and no latent heat. Now for this problem, we're doing a 1 hour calculation for the hour of 8 a.m. So, part of the cooling load is through the walls, from the outside to the inside, from another room to this room. And the basic rule for heat conduction is Fourier's law. The total heat going through the wall equals the heat transfer coefficient of the wall times the temperature difference. Very simple. That gets you watts per square meter, but really you know the area of the wall. That's here, so you just want watts. So for a simple example, if K of the wall is 0.5 and it's 30 degrees outside and 20 degrees inside, and the area of the wall is 15 meters squared, the heat transfer through the wall is 5 watts per meter squared, or total 250 watts. So you can practice this now, I hope. Let's move on. Now in this case, for this room, our set temperature is 26. This wall is a concrete wall, and the heat transfer coefficient is 0.63. And we know the area of the north wall and the east wall. But we need the outdoor temperature. So we're doing a case for Tokyo. And these are some kind of average temperatures. These are temperature, dew point temperature, and absolute humidity for summer in Tokyo. So we want the outdoor temperature, and our problem is 8 a.m. So we'll use this. 28.9 degrees is the typical outdoor temperature at 8 a.m. in Tokyo in summer. So we can use this equation. We know the area of the wall, the temperature difference, and calculate here. But there's also the sun. Now the sun will heat the wall, and that will make more heat coming into the room. So we can't do this simple calculation. We have to account for the sun. Now if the wall is thick, the sun will heat the wall, and a bit slowly the heat will build up, and then the total heat will become bigger later. But if the wall is thin, the heat will build up very quickly and go through the wall very fast, and there'll be more heat probably going through the wall. So the total heat through the wall partly is the temperature difference here from the original equation, but also this solar load, which changes with time, and it depends how thick the wall is and what the material of the wall is. It's very complicated. We could also write this with delta T here. Now that's a really complicated calculation, so instead there's this equivalent temperature difference. This plus this is the same as AKW times ETD, the equivalent temperature difference. The equivalent temperature difference is both this plus this together. And it's all factored in by professionals into a chart. And you can use this chart to get the temperature difference plus the solar difference at the same time. Now for 8 o'clock, again in Tokyo, in summer, now this depends on the wall. We're using this wall, a 150 millimeter typical concrete wall. On the north side, it's 2.4 because sun does not reach the north wall very well. The east side is 4.9 because the sun at 8 a.m. is hitting the east wall. So, for this wall, the north wall, there's a window, but the walls, with the sun hitting the walls, this is the equation. The heat transfer is the area times the heat transfer coefficient times the equivalent temperature difference. And we'll go through. We know this. We found this on the chart. We know the area. And we calculate the north wall is 52 watts. For the east wall, we use the different ETD. Same wall. For K, ETD is 4.9. The area is this. And through the east wall is 57 watts.